Hello student, in previous lecture we have discussed two important theorems to check whether given sequence is convergent or not. The first theorem says that if your sequence is monotonically increasing sequence and if it is a bounded above, then sequence is converges to its least upper bound. Or the second theorem says if your sequence is monotonically decreasing sequence and it is a bounded below, then given sequence xn is converges to its greatest lower bound. For an example, consider an example. Show that the sequence xn defined by x1 is equal to under root 2 and xn plus 1 is equal to under root 2 xn converges to converges to 2. Such a type of example can be solved by using previous two theorem. Either you can show this sequence is monotonically decreasing or it is a monotonically increasing. If it is a monotonically increasing, show that it has a upper bound, or if it is monotonically decreasing, show that it has a lower bound. Okay. Now to check whether it is a increasing or decreasing, what is the first term? Recursive function is given. If you want to determine the next term of the sequence, you have to put the value of n here. Okay, so if you put x1 is already given, x1 is equal to under root 2. What is x2? In place of n, if you put 1 here, then x2 is equal to under root 2 x1. But what is x1? x1 is under root 2. x1 is equal to, so x2 is equal to 2 under root of 2. Now, from these two number, whether x1 is less than x2 or x2 is x2 is less than x1, we want to decide. All of we know that 1 is less than 2 under root 2. 1 is less than under root 2. 1 is less than 2. 1 is also less than under root 2. This implies 2 less than 2 under root 2. If you multiply this equation by a positive number, then this inequality sign remains same. So 2 less than or equal to under root 2. This implies under root of 2 less than or equal to under root of 2 root 2. Under root of 2 root 2. So what this implies? But what is root 2? It is x1. Now what is under root of 2? Again under root of 2, it is what? x1 less than or equal to x2. So x1 less than or equal to x2 means what? We want to show that this sequence is a monotonically increasing sequence. Now, if you apply, since given statement contain set of natural number, and if you want to prove your result for n terms, then you have to apply first principle of mathematical induction. Already for n equal to 1, we have proved our result. This is for n equal to 1. You can say that result is true for n equal to 1. Now we assume result is true for n is equal to k, means what? sk is less than or equal to sk plus 1. We assume this, and in step number 3 we want to show that result is true for n is equal to k plus 1. Result is true for n is equal to k plus 1. That is, we want to show here sk plus 1 less than or equal to sk plus 2. Okay. Now, from step number 2, what is given? sk less than or equal to sk plus 1. Now, multiply this equation by 2. If you multiply by positive number, this inequality sign remains same. That is 2sk less than or equal to 2 times sk plus 1. And if you take the square root, then square root of 2sk less than or equal to square root of 2sk plus 1. But what is square root of 2sk? From this term, you can write square root of 2xn is what? Xn plus 1. So what is square root of 2sk? It is what? Sk plus 1. And what is square root of 2sk plus 1? It is equal to sk plus 2. Sk plus 2. And therefore, by using first principle of mathematical induction, we can conclude that the given statement, this statement is true for all n, or it is a monotonically increasing. Or this implies, by using mathematical induction, we can write xn less than or equal to xn plus 1 for every n belongs to natural number. Okay, so this statement is true, but if this is true, means what? Given sequence is a monotonically increasing sequence. This sequence xn, is a monotonically increasing sequence. This implies xn is monotonically increasing sequence. Now in step number 2, we have to show that this sequence has an upper bound. Okay, so what is given here? Since xn is less than or equal to xn plus 1, but what is xn plus 1? What is xn plus 1? Value of xn plus 1 is xn less than or equal to under root of 2xn. Okay, if you square on both sides, this inequality sign remains same. So if you square on both sides, xn square less than or equal to 2xn. If you take this 2xn right hand side term on the left hand side, you will get xn square minus 2xn less than or equal to 0. Now take xn is less, xn outside, so it is what? Xn minus 2, which is less than or equal to 0. Now when the product of two numbers is less than or equal to 0, if both have an opposite sign, that is, if this is a plus, this is a minus, then it is less than or equal to 0, or if this is minus, this is plus, then it is less than or equal to 0. But what is xn? First term is root 2, so it is a greater than or equal to 0. So xn is greater than 0. Xn is greater than 0. That is sequence. Every term of sequence is greater than or equal to 0, not greater than or equal to. X1 is root 2, and it is a monotonically increasing sequence. Means what? X2 is also greater than 0, X3 is also greater than or equal to 0. So each term is greater than 0, and product of these two terms less than 0 means what? This term should be xn minus 2 should be less than 0, less than or equal to 0. But what this implies? Xn is less than or equal to 2. Means what? For every n. Means what? Xn has an upper bound. Okay, look here. Every term of the sequence is less than or equal to, means what? Sequence xn has an upper bound. X2 is an upper bound for this sequence, and therefore xn is what? Bounded above. When we say it is a bounded above, if it has an upper bound, it is what? Bounded above. And therefore, from the previous theorem, we can conclude that since sequence xn is a monotonically increasing and it has an upper bound, and therefore it is bounded above, therefore sequence xn is a convergent sequence, and therefore we can write here, since xn is monotonically increasing sequence and bounded above, therefore it is convergent sequence. It is a convergent sequence. Now it is a convergent sequence. Next step is what we want to show, that this sequence xn is converges to 2. This sequence xn is converges to 2. We know that if xn is converges to L, then xn plus 1 is also converges to L. Okay. We know that if the sequence xn is convergent to L, then xn plus 1, xn plus 2, xn plus 3, all these sequences also converges to L. For example, xn is equal to 1 upon n. We know that this sequence is converges to 0. Then xn plus 1 is 1 upon n plus 1 is also converges to 0. We are going to apply this logic to determine the limit of this sequence. Now since suppose limit n tends to infinity, xn is equal to L. Okay. So this implies then which is same as limit n tends to infinity xn plus 1. Okay. So we know that but xn plus 1 is equal to under root of 2xn. So if you take limit n tends to infinity on both sides, what happened? The value of this term is equal to L and the value of this term is under root of twice L. If you take the limit n tends to infinity on both sides, the value of this term is also L and value of this term is also L. So it is, if you square on both sides, you will get L square is equal to twice L. Take this twice L to left hand side, minus twice L is equal to 0. But this implies L minus 2 is equal to 0. But again, L is never 0. Okay, again if you see the previous video, you can you can observe that if the xn is greater than or equal to 0, if xn is greater than 0, then its limit is also greater than 0. Okay, limit is also greater than 0. So L is never 0. This term is never 0. This term, since L is never 0, implies what is 0? What is 0? L minus 2 is equal to 0. But this implies L is equal to what? 2. And this is what we want to show, that what is L? L is nothing but the limit of the given sequence. And therefore the given sequence, this sequence is converges to 2. Hope you understand.